quantum mechanics, network analysis, image processing, machine learning algorithms, circuit analysis, or other systems. These are some of the fields where metrics are used for understanding or analyzing different systems.
Hello, I am Atikur Rahman. I am an undergraduate student of Department of Electrical and Electronics Engineering, University of Chittagong. In this presentation, I am going to explain the application of matrix. This presentation video is from the course Math 361, which is Complex Variable, Integral Transformation and Linear Algebra. And my course instructor is Mohammad Zaid, lecturer, Department of Electrical and Electronics Engineering, University of Chittagong. So let's begin. So the first question is, why about the application of matrix? Because without knowing the real life application, it is quite boring to learn matrix subject in this math course. In this presentation, I am not going to explain the different types of matrix. Rather, I will explain the real life applications of matrix with some interesting examples. For example, let's see what happens when we multiply matrix by a vector. When a vector starts at the origin and ends at 1, 1 can be written as shown. When we multiply 2 by 2 matrix through the multiplication rule, we get a new vector out in the case of 1, 3. So, we let a vector in and the matrix is scaled and rotated to get a new vector out. Different matrix will rotate and scale the vector differently. Another example of a simple matrix which just rotates the input vector like this. On the other hand, this matrix thus scaled and vector goes in and comes out twice as long. But not all the 2 by 2 matrices are simple as that. Like matrices are rotated and scaled differently. Here, this transformation is linear and this is why we call the subject linear algebra. Matrices are extensively used in linear algebra for solving systems of linear equations, calculating determinants, finding eigenvalues and eigenvectors, and performing various transformations such as scaling, rotating, and reflections. If you notice, the interesting part is that one of the vectors is scaled, not rotated. This would happen to any vector on the line as we can see. Eigenvector. Any vector that is not only scaled by matrix is called an eigenvector, and the scale factor is called the eigenvalue. Maybe the first application we learn about matrix is how to solve the equations by using the matrix. For example, applying the Kramer rule. In the two given questions, coefficients go to matrix, variables go to another, and output goes here. From the previous example, we can see by applying the inverse matrix process, the value of x, y which satisfies the upper equations, which is 1, 1. And this is the solution. We can use matrix in circuits and electronics because in a complex circuit, the voltage and currents are unknown variables. By applying the inverse matrix, we can find voltage and currents in the circuit. Now, let's talk about another example. Imagine at the time of virus infections in a place where the place is quarantined, so the population of the place remains same. Let's say in every hour, 20% of the villagers are getting infected by the virus. Luckily, by the vaccination process, 10% of the villagers are curing. So, we can say the system is continuously evolves over time. Now, the question is what will happen in the long run? Let's see what will happen in a situation where 50% of the villagers are infected. Here, for the first hour, 80% of the remaining villagers remain secure. With the cured 10% of the infected people, total of 135 villagers are staying in the not infected site in the first hour. Now for the infected site, 20% of the villagers are newly infected and 90% of the remaining people which are not cured, giving a total of 165 infected people for the first hour. Here the total number of the villagers remain the same, which is 135 plus 165 is equal to 300. But what about the long run? Here we have some linear equations that can be represented by a matrix of those percentages that don't change. This is multiplied by the input H and G. And we have the number of villagers after the given hour. This is called the Markov matrix by the way. since its column sums to 1 and has no negative values. Now, the first input was 150, 150, and after 1 hour of multiplication, it gets moved to 135, 165. After 2 hours, apply another transformation, sending it to 125, 175. We can ask a question, where actually the vector moving? By looking closely, we can see that this vector or anything on this line is takes 4, while others moving towards it. This vector is the eigenvector of the matrix and the eigenvalue is 1, since it does not scale. Since it does not scale and rotate, it is the equilibrium of the system and therefore the answer to our question. After a long time, the numbers of the cured and infected villagers will be settled. Two numbers which lies in the time and add to 300, which would be 100 for the cured people and 200 for the infected people. So we can see this kind of math could be used to analyze how a virus will spread throughout a population, for example. Also, Google PageRank algorithm involves this Markov matrix. Digital image processing. Matrices are extensively utilized for various image processing and operations like image representation, filtering and convolutions, transformations, compressions, color space conversions, morphological operations, feature extraction and pattern recognition, image restoration. Analysis of a single image. A square pixel made up of a 1 million pixels, 1000 on each edge, could be represented by 1000 by 1000 matrix, where the entries are the color values of each pixel. Working with black and white pixel is much easier because we can represent black pixel with a 0 and white pixel with 1. On the other hand, about the grayscale image, anything between 0 and 1 can exist, which will correspond to a different shade of gray. Let's make a blur image. The process we are using here is kernel image processing. Let's mathematically blur this image of number 1. Now, by using a 3 by 3 matrix where every entry is 1 by 9, this is known as a kernel and image processing. Now, by the process here, we can take the sum of the set, the center pixel of that color in the new image. After mapping each new number to the blurred image, this will be the values. Now, by applying the color in the pixels based on their values, we get a blurred image of the number 1. Here, the kernel took the sharp edges in the original image between black and white and smooth or average it. The type of blur is called box blur. And from the Wikipedia, we can get more examples. 1. There is box blur. This is the output. 2. The Gaussian blur 3 by 3 and the Gaussian blur 5 by 5 also blur the image. 3. There is a sharpened kernel. 4. Edge detection kernel for the sharp change in image processing and manipulations. Whether it be blurring an image, detecting edges, or sharpening an image, it all comes to manipulating the pixel in a very specific way. Computer graphics, projection of a 3D object on a 2D plane, we can use the matrix math to map the 3D points and find where they would appear on the flat screen. If we look at the network and graph theory, we can see the use of matrix from the person spreading the virus infections to the 9/11 attacks. Matrices play a significant role in machine learning algorithms, especially in tasks such as linear regressions, logistic regressions, neural networks support vector machines. The Hill zipper is a cryptographic algorithm that uses matrix for encryption and decryptions. In this method, plain text is divided into blocks of fixed size, and each block is converted into a numerical representation. These numerical representations are then multiplied by a fixed matrix modulo. the size of the alphabet to produce a ciphertext. In summary, the video has shown how matrix is used in different areas. Whether it's making computer graphics, analyzing data, or solving problems in science and engineering, matrix help us organize information and find solutions. From drawing pictures to understanding complex systems, matrices are a powerful tool that people use every day.